Good morning. This is Hope Reactor. Now, let's begin today's news.
Could dirty factory water become fuel? Japan's new reactor turns waste into methane. What if the dirty water leaving a factory could help power the same factory? Industrial wastewater is usually treated as a cost. It must be collected, cleaned, and safely discharged. Solid waste may need to be dried and burned. That requires energy, equipment, space, and money. But researchers in Japan are asking a different question. Instead of only asking, how do we get rid of this waste? They are asking, what energy is still trapped inside it? On July 8, 2026, researchers from Japan's National Institute of Advanced Industrial Science and Technology, known as AIST, and Kagoshima National College of Technology, announced a new reactor that can treat solid, organic waste and high-strength wastewater together. The reactor operated continuously for more than 100 days, and its methane production rate was 1.62 times that of a conventional reactor. This could turn the end of manufacturing into the beginning of an energy cycle. The technology targets waste from biomanufacturing. Biomanufacturing uses microorganisms or enzymes to produce chemicals and materials. Plant resources can be broken down into sugars that microorganisms use as raw material, but even cleaner production creates waste. Not all plant material becomes sugar. Solid residues containing cellulose remain. The cultivation process also produces wastewater rich in sugars, organic acids, alcohols, and other organic compounds. Solid residues are often dewatered, dried, and incinerated. High-strength wastewater is commonly treated with oxygen-loving microorganisms, which require air pumps, electricity, and large tanks. So a process designed to reduce environmental impact can still create an expensive and energy-intensive waste problem. The Japanese team turned to anaerobic digestion. Anaerobic means without oxygen. Inside this system, different groups of microorganisms work in sequence. One group breaks large materials such as cellulose into smaller molecules. Another converts those molecules into organic acids. Finally, methane-producing microorganisms transform those compounds into biogas. It is not one microbe performing a miracle. It is a microscopic relay team. But conventional reactors struggle to keep this relay moving. Solid material may not mix well with the microorganisms that can break it down. It can settle and accumulate inside the equipment. If organic acids build up too quickly, the water becomes too acidic. Methane-producing microorganisms can weaken and gas production can fall. The microorganisms need the right environment, in the right order. That is the idea behind the new ABCS reactor. ABCS stands for Anaerobic Baffled Continuous Stirred Reactor. Its interior is divided into two functional zones. The first is a stirred section. Here, solid waste is mixed with microorganisms. This helps cellulose-degrading bacteria convert large materials into smaller compounds, such as glucose. The second is a baffled flow section. Partitions guide the wastewater through several compartments. As it moves forward, smaller compounds are further broken down, and methane-producing microorganisms complete the process. A gentle slope connects the sections and helps prevent solids from becoming trapped. The breakthrough is not brute force. The reactor uses its shape to create a biological sequence. First, break down the solids, then process the smaller compounds, finally produce methane. To test the design, the researchers operated the ABCS reactor beside a conventional anaerobic, baffled reactor without the stirred section. Both systems received the same simulated solid waste and high-strength wastewater for more than 100 days. In the conventional reactor, cellulose and other solids were not adequately broken down. They accumulated inside the equipment. The treated water appeared cleaner, but some material was trapped inside the reactor. Over time, that buildup could block the flow path and cause failure. The ABCS reactor behaved differently. Its stirred section helped microorganisms break down the solids. More material moved into the later stages and contributed to methane production. The system remained stable for more than 100 days, and its methane production rate reached 1.62 times that of the conventional reactor. The researchers also analyzed the microbial communities. Both reactors contained microorganisms that convert organic acids into methane. However, the ABCS reactor had a higher proportion of bacteria associated with breaking down cellulose and glucose. The design did not force the microorganisms to work harder. It created an environment where the right microorganisms could grow and perform the right jobs. The machine is not the true worker. The microorganisms are. The reactor is the workplace designed around their strengths. If this technology can be scaled successfully, it could combine solid waste treatment and high-strength wastewater treatment in one system. That could reduce space requirements and improve efficiency. The recovered methane could be used for heat or electricity, allowing some treatment energy to come from the waste itself. A treatment facility could begin to act as a small energy recovery site. A cost could become a resource, but this technology is not ready to transform every factory tomorrow. The current results came from simulated waste. Under controlled research conditions, important questions remain. Will the microbial balance remain stable in a larger reactor? How much will construction, maintenance, and monitoring cost? Can it handle real factory wastewater that changes every day? And will the recovered methane justify the investment? The researchers plan to scale up the reactor for demonstration, tests, and study waste from plastic chemical recycling. So the wastewater problem has not been solved, but researchers have built a promising bridge between waste treatment and energy recovery. More than 100 days of stable operation and a 1.62 times methane production rate are not the finish line. They are evidence that the idea deserves the next test. When we look at dirty water, we see something that has lost its value. Microorganisms see carbon, nutrients, and molecules that can still be transformed. Perhaps sustainable industry will not depend only on producing less waste. It may also depend on recognizing the value that remains after production ends. Invisible microorganisms, human engineering, and a system that gives both the correct role. Together, they could turn wastewater treatment from a necessary expense into part of a factory's energy strategy. This is Hope Reactor, where hidden ideas become practical hope. How far should factories go in producing energy from their own waste? Share your thoughts in the comments and subscribe for more technologies that could quietly change our future.